All right. So we looked at the conditional independence, right? We looked at computing all the independence relationships, and then we saw that what might be the sweet spot, or what you might have to look at within your Bayesian network from a logical point of view also to identify the most suitable or most appropriate conditional independence relationships within your Bayesian network, within the graph. But one thing that you will have to remember that it's a graphical acyclic, probabilistic model, Bayesian network. The difference between Bayesian, to answer your question, Ronald, from last week, the difference between the Bayesian network and constraint satisfaction problem is that although they look very similar, they have a lot of similarity among each other because both have nodes, right, and arcs. They both can solve, query problems or basically assignment problems, variable assignment problems. But one thing that the CSP doesn't have is the uncertainty. Within CSP, we just simply apply a backtracking or a search algorithm and to solve that problem without even looking at the probabilistic, or uncertainty or the probabilistic independence relationships in constraint satisfaction problems. What we have in Bayesian networks is that they not only identify the conditional independence, relationships, but it also can solve probabilistic queries, probabilistic where you have uncertainty. Within CSPs, we don't look at uncertainty. Yes. So if you look at the top, the relationship from Y to X and Y to Z is not that condition. So if you look at it from a point of view of a real world scenario, by saying like Y, X, and Z, it's saying that if Y happens, then there is some probability that X will also happen and Z will also happen. Okay, so these are, remember, random variable is an event whose outcome is unknown. So those are random variables. You can also say that they can be transitions like MDPs, right? Yes, states. Orthogonal, that's independence relationships. X is independent of Z given Y. So remember, this was the common cause. This was the common cause, number 2 conditional independence rule that we had. So, and the second one is the causal chain, if you remember, causal chain, X to Y to Z. And then we had, I don't have the common effect. Common effect looks something like this. X and Y, they both impact Z. That's the common effect. That just has a V structure. If you look at it, the one that I drew, it's just a V structure. So both the parents are actually pointing to the child. So the parents are the causes and the child node is the effect. So that's why we say common effect. Common effect is the strangest one, if you remember. Okay. All right, causal chain, common cause, and common effect. Remember that because it will help you guys solve several problems in your exam and your homework too. So this is the canonical example that we covered very briefly in our class, right? Where we said it's an alarm network, and we saw conditional independence relationships in the alarm network, and we saw basically the conditional probability distribution tables that basically sits behind each of these nodes in here. So we looked at an example, right? Something like this: alarm, burglary, earthquake, Danny and Todd, the 2 neighbors that we have, right? So behind each of this node, there is a conditional probability distribution or conditional probability table, CPT, that sits, that represents all these, probability or all these relationships. Each row is a specific conditional dependence relationship that you have, okay? The specific probability with which certain event may or may not occur, okay? So, oh, what did I have? I think I had a video. Oh yeah, I'm saying that each table, each node has a conditional probability table behind it. I just recorded a short video. So we have 8 entries. So because these are the Boolean variables, they have 8 entries, right? 2 to the power 3. Okay, 2 to the power 2, etc., etc. So what we also covered was that now we looked at the inference, I think quite a few times in the previous lectures, is that to solve a specific problem or to solve for a query, what we do is there's one way to solve that problem is by inference by enumeration. What we do is we look at the giant probability distribution table, right? And we take the steps. Suppose that something like this. So there's a general case that there are some evidence variables and there is a query variable. So we want to query about some variable, saying like, what is the probability that the traffic is high given rain? Okay, something like that. All right. So there are some query variables, there are some evidence variables, and then there are some hidden variables too. The reason why hidden variables exist within your query is because of the connections. You may only say that there's a query variable given some of the evidence, but between those or even beyond their domain, there might be some links within your Bayesian network that may have hidden variables. So you'll have to have the hidden variables included, solve for those hidden variables in order to answer the query. And what we do is we take the steps, something like this. What we do want is that we want to get to this stage where we say that we have the probability of the query variable given several evidence variables. Okay, so in order to solve for this query, we would have to sum out the hidden variables one by one, the hidden variables that we have. So what we saw in the previous lectures was that from the joint distribution, we select the entries that are consistent with the evidence. Remember, we said that only look at the query variables and also the evidence variables where the evidence is given. Okay, something like the probability that it is hot given it is sunny. Okay, probability of, let's say, weather, hot or cold, given that it is sunny, meaning we are ignoring the rainy part, right? So we are going to look at the probability distribution table, remove all the rows that has rain in it because we are looking at the sunny, right? We are looking at the evidence. So the first step is to select the entries that are consistent with the evidence with E1 to EK, then sum out the hidden variables to get the joint of the query and evidence, because this is what we are looking at, what we want, right? Something like this. So the joint distribution, we look at the joint distribution, right? And we're going to sum out for all of the hidden variables that we have so that we can ignore or remove, not ignore, basically. Remove all these hidden variables from our query to get to this point, because this is what we are trying to solve, right? Because this is what is in our actual question. So we would sum out for hidden variables, and then we will calculate the normalizing constant, the z value, right? Once we have the smaller table, we calculate the sum of these, right? And then we divide each entry by the sum of these. So that's the normalizing constant, because the probabilities, sum of the probabilities has to sum to 1, right? Of this newly designed table that we have. So this was actually inference by enumeration. We'll see first why inference by enumeration in Bayesian network is going to be extremely difficult to compute because of the network structure. Something like, we have the alarm network example once again, right? And now suppose that we want to find the probability of burglary plus B or minus B, right? Whether or not there is a burglary, given that Danny and Todd both called me, right? Like plus D and plus T, they actually are the instantiations, right? Instantiations meaning that, so the capital letter is for a random variable. but then the lowercase letters are actually the instantiations of those variables. So plus D means like Danny calls, minus D means Danny doesn't call, right? So we assign instantiations. What that is actually equal to is the proportional to the joint distribution of the burglary plus D and plus T. So we have the evidence, right? So what that proportional sign in B means is that we have to scale that, rescale it, right? We have to get from the larger distribution table, joint distribution, we have to get the smaller distribution of only the B plus D and plus T, and then we have to normalize those, get the basically the entries, get the sum of the entries, the normalizing constant Z, and then divide that by Z. That's all what it means, that time. If you look at this structure on your right, that actually is equal to this part, the sum of P, B, E, and A, and given D plus D plus E. Why do we have E and A? Because of the Bayesian network structure, we have these two hidden variables, E and A. Because if you look at plus D, if you write down the probability according to this Bayesian network, it will look something like this, right? Probability of B, it doesn't have any parent if you look at the Bayesian network structure. Probability of E, let's just not worry about E at this moment first. Look at the D plus T. So we will look at the plus D, but D is dependent on A, right? So we have A, probability of plus T. T is also dependent on A, and now A is in output. A is the hidden variable. So what does A depend on? A depends on both B and E. So we have to include A, probability of A, alarm given that there is burglary or not, and the earthquake, right? And we have to include the E also. That's why we have included P of E. By looking at this probability, the Bayesian network, we come up with this formula, right? Now, there are two hidden variables. By hidden variable, I mean that they don't appear in the query that you have, right? We're looking at the query, probability of B given D plus T plus T. So they don't appear in the query variable, but you will have to, when you have to get the joint distribution, they will appear because of the conditional independence or because of the relationships from the Bayesian network structure that you have, right? So this, you will calculate this, and now you will have to sum them out for, all their instantiations. So suppose that if they are both are binary here, we will have to sum them out for plus E minus E and then plus A minus E, right? Does that make sense? Because we have to sum out for all of those entries. Now look at this. So if I expand this sum, so this entire equation will be written for plus E, okay, plus A, then plus E minus A. So this is for E plus E, and then we have minus E plus A, and then minus E minus A 4 times, because we will have to sum them out for all their instantiations. Now suppose that if there were 4 different types of entries, then you would have to write this about 8 times, right? So this is for B, right? We're calculating for B, burglary. So that means we will have to also calculate for burglary plus B and minus B also. So you will have to do this computation twice, right? For just this simple query. This computation, one for plus B and one for minus B. One for the burglary and one for not burglary, right? So you will have to do 1, 2, 3, 4 computations twice to get to your query, right? So what is causing an issue or the problem here in our Bayesian network structure is actually all the hidden variables, because we have to sum them out. So the more hidden variables you have in your Bayesian network, the harder it is going to be for you to do the computation. Something like this, we looked at the example, I think last week, very brief example like anti-lock. What is the probability of anti-lock given all the observed variables? There were about 13 observed variables or 13 unobserved variables or 13 hidden variables, right? So we will have to sum all those 13 hidden variables. Assume that they are binary. assume that they are binary variables. So if there are 13 unobserved or hidden variables, you will have to do 2 to the power 13 computations to just get this small query solved. Ronald. Yeah, there are arcs. Yes. All right. So why is inference by enumeration really slow? Is really slow. So what we do is we join up the whole, joint distribution before we sum out. So suppose why is inference by enumeration is slow? Because remember we said that in step 1, we look at the giant joint distribution. We may not have that. What we have to do is we have to get the marginal conditional distributions, join them together, all of them together with respect to all the unobserved or hidden variables, join them all together to get the large joint distribution table, right? And then from that large joint distribution table, we ignore or take out the rows, take away the rows that don't have the evidence. So we actually join all of them together, get all the entire giant joint distribution table, and then solve for the query, which is why it is very, very slow. It can get very, very slow. Okay. So in order to have a more efficient, computation, what we will have to do is, even in inference by enumeration, we do the joining and then summing out, right? Operations. So we do the join operation, multiple join operations, and then we do multiple elimination or sum out operations. When we sum out for hidden variables, that means we are eliminating them from our query, right? Make sense? So what we are doing is basically just the 2 types of operation. We're joining multiple conditional distributions, all right? And then we are summing out or eliminating multiple variables. So in inference by enumeration, we join all of them together, all of them first, and then one by one sum them out, sum the hidden variables out. If we interleave these join and eliminate operations in a slightly different way, as compared to inference by enumeration, we can get a much faster computation. Okay, and we will see how we can do that. And that's called variable elimination algorithm. Okay, so it is still NP hard, but usually it is much faster. So there is no single way to identify or to find out what is the best way to interleave the join and eliminate operations that will give us the fastest possible way to solve a query. There's no one solution. But usually, if we do interleave these join and eliminate operations, we can get a much faster response, much faster solution to the queries, and we will see that how we can do it. I think we went over this example too, that first of all, in order for us to have interleaved joint and eliminate operations, we'll have to look at different factors. What are the different? Okay, by factor, whenever I talk about factor, it means it's a small conditional or local conditional probability table. Every time you talk about factors or you see the word factor, I'm talking about the local conditional probability table. What do you mean by local conditional probability table? The conditional probability or the CPT of a node or a variable given only its parents. That's it. That's the local, not using the chain rule. So far, so good? So we have to look at different factors or different local conditional probability tables so that we can identify those and then see how we can join them and eliminate certain variables in a specific order. Make sense? In a specific order. We'll have to find out how so by inference, by enumeration, we saw that we have to join all those local conditional probability tables first, get the joint distribution, and then from the joint distribution, we only look at the rows that are consistent with the evidence. And then we sum out the hidden variables, and then we get to the normalizing constant, and then finally we get the answer, right? So we are actually going backwards by looking at all the local conditional probability tables and joining them together. That operation can be very, very expensive. What we will. kind of recursion, but yeah, we are actually doing multiple joins together. Okay, so the idea is to not join all of them together first and then do the sum out. How can we do like some join first and then sum out, then some more joins, then sum out, something like that, another order. So in an order, we will have to join different conditional probability tables. So first of all, we have to identify what are those different local conditional probability tables, right? And we will name them factors. So one factor is basically a joint distribution. Just like how we saw before, from a large table, we look at just the joint distribution, something like probability of X and Y, or probability of temperature given temperature and the weather. We have seen this before, right? And they sum up to 1. So all the instantiations of 2 variables together. So first of all, this is joint distribution that we can, one factor that we can see. And we have been seeing it quite a number of times before. Okay. Another one is the selected joint, where a slice of joint distribution or entries of P of X and Y for fixed X, because we have given the evidence there, because this is the small, lowercase, and all Y. And that sums to P of X. Something like this. Now, instead of the T, we have the evidence at T, evidence at temperature. All what we will have to do is, you see, we only look at the weather code from this table, right? And we get the last 2 rows. That's one, right? Selected join. Make sense? Only look at the rows that are consistent with this evidence, because we have given the partial evidence now. So these are 2 types of factors that we have. All right. And we also looked at single conditional. Suppose now that after the conditional bar, you may have some evidence. Right? You may have some evidence. Something like probability of all instantiations of Y given an evidence at X. So that also sums to 1. Something like this, cold, probability of weather given cold. So we look at only the rows that have the cold, like this, cold and sun and rain. We get the sum of these 2, right? And then we divide each entry by the sum of them, which is by 0.5. So that's another factor that we can have. Then we can have family of conditionals, probability of X given Y. That is multiple conditionals, right? That also has to sum up to Y, something like this. So we look at the probability of weather given temperature. And we say that probability of weather can be hot and cold, and weather can be sunny and rainy. Okay. So each of this, as you see here, probability of some given Y. So if you look at temperature hot, the sum of these 2 rows is going to be with respect to probability of weather, sun and rain. And this is going to sum up to 1. And this is also going to sum up to 1. So that's family of conditional. Remember, joint distribution, selected conditional, single conditional, and family of conditionals. These are 4 different types of factors that we have. Okay. And then the 5th one is specified family. Specified family, probability of some instantiation of Y given all instantiations of X. So it will look something like this. Probability of rain given hot. So, and probability of rain given cold. So we are only looking at some of the evidence, okay, given the temperature or unobserved variable that we have behind the bar. All right. So we have multiple different factors. Now, actually, we can get all these different types of factors, and we can perform some of the joining and some of the elimination operations instead of doing the inference by enumeration. And we will see how this can be a much better solution. Suppose that we have this network, causal chain, right? It's a causal chain. Probability that it is raining or not raining, given raining, that there might be traffic, heavy traffic, no, or maybe yes or no in this case. And then you might be late for the class, right? How will it look like? Okay, so there is only 10% chance that it might be raining. Okay, so you get actually the conditional probability distributions, the conditional probability tables at each of the node. Remember, we said that from this Bayesian network structure, behind each node, there's a conditional probability table that sits in there. Conditional probability, L given T, because of the Bayesian network structure, right? So suppose that we have some numbers here. Let's look at what are the different factors that we can find from these, okay? In order to solve the query like this, what is the probability that, probability of L, you're being late in the class or not? If you look at the inference by enumeration, and by looking at this Bayesian network structure, don't you have to sum out for R and T? Because R and T are hidden variables here, right? L depends on T, and T depends on R. So you will have to sum out for R and T to get this, probability distribution. And if you look at this Bayesian network structure, you will have to give the probability of R, then probability of T given R, then probability of L given T. So now you will have to do basically one for plus R, one term for plus R, one term for minus R, another term for plus T, another term for minus T. 4 terms, and you will get the probability of plus L. And then you will have to do the same computation for minus R, or you will do one minus plus L, right? Because if it is binary, then you can get that. But you will have to expand all of those, right? What you're doing is you're joining for R and T together, right? And then you are summing out with respect to R and T to get to the probability of L. That's inference by enumeration. Something like this. I think we saw this example too, right? So now suppose, okay, so then we have basically a specified conditional. Suppose that you have the evidence. Now, suppose that you want to say, what is the probability that you are late to the class? What do? You look at the same probability tables and remove the entries that do not match with the evidence, that are not consistent with the evidence. So by looking at all those 3 probability tables, now that we have the evidence, L equals plus L, all what you have to do is we'll just have to come up with a new, but a smaller probability table by looking at only the plus L, the rows that are consistent with the evidence that we need. So as soon as you give the evidence, right, it's the same procedure as looking for the factors, but the smaller ones where only within the conditional probability tables, look for the probability tables that have the random variable and pick out only the rows that match the evidence. L equals plus L. That's it. Okay. So even if you have evidence, you can still perform, but you can still look at the evidence and then perform the same operation, inference by enumeration. Right? I think we saw quite a few slides. What is the conditions that allow you to sum out? Sum out. Remember this? You have to do the sum. So you see, we are summing with respect to R and T, and we have to expand this equation 4 times. One for plus R, one term for minus R, one term for plus T, and one term for minus T. So you're summing out, you're removing the hidden variables out of your equation. That's elimination. And joining is basically multiplying. Joining is multiplying different conditional probability tables together, and then eliminating or summing out. Eliminating meaning summing out the hidden variables. We'll see some of the examples, and I think it will make much more sense. So by joining, what we meant was multiplying 2 conditional probabilities together, right? Something like this, probability of R, and then we have probability of T given R, if we look at the Bayesian network structure. All what we have to do is look at the consistent rows within 2 tables and multiply them together. Something like this. P of R and T is actually equal to P of R times P of T given R. Because if you look at the Bayesian network structure like this, look at this Bayesian network structure. we have P of R, three conditional probability tables, right? P of R, P of T given R, because we have this Bayesian network structure. Then P of L given T, right? If we want to compute the joint distribution of P of R and T, we'll simply have to multiply their conditional probability tables together. And how do we do that? We look at the consistent, rows like plus R plus T. We look at the plus R plus T here, and then we look at the plus R, and we multiply these two together. 0.1 times 0.8, and then plus R minus T. We're still looking at plus R, so we will have to multiply this term with 0.2, right? And we simply fill the table in. That's the joint distribution, P of R and T. So we have done one join, right? We have done one join together, P of R and T. We have got a new table. All right, we're done with P of R and T, right? And then okay, so this is another, the same thing we have done so far. What we have done here is we have joined R and T together. And now we will have to join RT with L together, right? All right.
Let's go plus positive. Probability of
it did. So that one is 0.8. If you look at P of T given R, and here is 0.08 because we multiplied. We're joining R together. And now we'll join T because you see these both tables, we have T, right? And we have to join for T, and then finally we will have to sum out for R and T. So we will join R and T together. All what we mean is we will have to look at the consistent rows here and consistent rows here, and we will just simply multiply them together like this. So we will have R, T, and L this time, plus R, plus T, plus L. This term is coming from plus R, plus T, which is 0.08, and then plus T and plus L, which is this, 0.08 times 0.3, which is 0.024. Okay, just look at the consistent entries, that's it, consistent rows. Then we say the second row, plus R plus T minus L, which is once again plus R plus T, which is 0.08, and then plus T minus L, right? Plus T minus L, which is this one. 0.08 times 0.7, which is 0.056. We just multiply them together. Once we have that, and now we have the bigger joint distribution table. What were we looking for? Probability of L, right? Plus L, or plus L or minus L. So then what we will do is we will have to sum out for all of this R and T together and get the probability distribution of plus L or minus L. Right? And then we will just sum R, sum out over R and T. So what we do is elimination is simply the marginalization. We just have to find another projection that removes sums out over different hidden variables. Something like this. So you see P of R and T. If we sum over R, we just look at the consistent rows and just sum out over them. Plus T, and we sum these two together. Right?
we were already.
Yeah. So you see, we have eliminated R here. We're just one step back when we were doing the join over R, right? And now we're summing over R. Summing over R. I'm going to get back to the same example that we had from the previous slide. So this is just a small example. If you want to sum over a variable, all what you will have to do is look at the consistent entries and sum them together. That's elimination.
So marginalization is the same as sum.
Yeah. Yes. Okay. So you see, take a factor and sum out a variable. That's marginalization. That shrinks a factor to a smaller one, right? So then we can do multiple eliminations. If you have the giant distribution, like joint distribution, P of R, T, and L, sum out over R, right? Which is going to be 4 entries now. Plus T plus L, plus T minus L, minus T plus L, minus T minus L. And we will just have to simply sum out over R. So here it is going to be plus T plus L. Look at all the entries that have plus T plus L, which is this one, and this one, right? Just sum them together, and we will get the term. Then we will have minus plus T minus L, which is this one, and then this one. And we simply get the result. And then after that, we can sum out T and finally get our, by the way, this is 866. 866. We have just sum out over T. All right. Now, this is the most important, I think the most important slide for today's lecture. By inference by enumeration, all what we're doing is we're doing multiple joins together, right? We're doing multiple joins together, and then we are eliminating one by one. This is all what we have seen so far. Even in the previous slide, we look at the giant, from local conditional probability tables, we join them together by doing multiple joins, get the larger distribution table, joint distribution, and then we sum out several variables, eliminate one by one. It turns out that there is another way to do the join and eliminate. We really don't have to do all the joins first and then eliminate, because by doing all the joins, you're still coming up with the large, joint distribution. That's difficult. That's problematic for larger networks. What we can do is we can do some joins together and then eliminate some variables, then do more joins and then eliminate some variables together, and then joins. And so we just have to interleave the join and eliminate operations. This way, you can get much smaller conditional probability tables along the way. And by the end, you'll only be left with a really, really small table instead of a really big giant distribution.
So operation is fine.
Right.
Operations.
Joining the variables. And then operation 3 is eliminate. So find all the factors, join them together. If you're looking at inference by enumeration, join all of them together, then eliminate some. Eliminate the hidden variables. But for what we will do with the variable elimination, we'll join some of the variables together and then eliminate. So we actually interleave join and eliminate operations. And it turns out that this operation is actually exactly the same as this operation. It gives us the same results. It is something very similar to this. We have this formula, right? Like y plus z. It is actually equal to, xc, right? What we do with the inference by enumeration, we look at this thing, right? We join all of them together. We have the product, first, because that has, in arithmetic operations, it has a higher priority, right? We do all the products and joins together, and then we do the sum. It turns out that it actually is the same as this. So we're actually going backwards. For joining and elimination, we're going backwards. We join some of them together, we eliminate, and then do the product. Why is it in the what? Did I? I may not have mentioned factors as the number one operation. Factors basically is just like where you start with, and then you have two operations. You find the factors, right? All the factors, and then the first operation is you join them, and the second operation as the elimination. You eliminate them. I think this is why I may have mentioned as number two. Yeah, so you see here, operations. So there are two operations on factors. Factor basically is a step that you have to take within the example. So let's see how interesting it can be, this operation, right? So what we have to do is we're just like going backwards, finding out the join and eliminate together. All right. I think, okay, so we join over R first, right? And instead of joining over T now, we just eliminate R. So we join over R, P of R and T, we sum out R. So before going to the next step, joining over T, we just sum out R. How do we sum out R? We simply look at the consistent rows and we sum them out, right? By that, this is what we have just looked at. Yes.
Is it arbitrary which one you choose to sum out?
That's a very good question. I was actually going to talk about that. That's the problem within the Bayesian network. What variable do you have to choose to eliminate or to have to pick? This is a very important question. I'm going to talk about it in a few minutes. You're 2 steps ahead. Okay, so we have to sum out over R, right? And then we get the joint distribution. We join over T, and we basically get the 4 rows, right? And then we simply sum out T. Remember, nowhere in this operation we have a table that has 8 entries anymore. We have cut it to half by doing the sum before doing all the joins. So if we interleave the join and eliminate operations in some way, we can shorten the size of the joint distribution. And that actually gives us the same results. That's the good thing about variable elimination. No matter the way, the order in which you join and eliminate some variables, it is going to give you the same result. So the actual, by the way, join and eliminate, you can also do with the evidence. If you have the evidence, all what you will have to do is by look at this evidence. Suppose that now you have to do the compute discrete L given plus R. All what you will have to do is you take only those rows where the evidence is. Okay, and then perform this join and eliminate operations. Okay, so evidence, normalize, start. Okay, that is going to be the very important question. So general variable elimination. What you do is start with initial factors that you have, right? Start with the factors that you have found, and then pick a hidden variable. Pick one hidden variable, join all factors mentioning that hidden variable, and then eliminate that hidden variable. This is what we have just seen, the 3 steps before, right? In several previous slides. Take a hidden variable, and then join all the factors, and then eliminate. You know the reason why you cannot eliminate before you do the join? You will first have to look for a specific variable in all factors, in all conditional probability tables that you have to join them together, then you have to eliminate. If you don't do the join and if you eliminate, you're not going to have the consistent evidence because some instantiations of that hidden variable will be left within some of the other conditional probability tables, and your entire inference is going to be wrong. So you'll have to join first. But the actual question is, how do we pick that hidden variable? Based on what criteria do you have to pick that variable? One simple and straightforward answer might be pick up a variable that has the least number of parents, right? Or pick up the variable that has the highest number of parents, so that it gives us, well, if it has the highest number of parents, that is still going to give us a large joint distribution table, right? So pick up the variable that has the least number of parents. That is one way, right? In fact, picking up a hidden variable in Bayesian network or variable elimination algorithm is actually a search problem. You have to search for all the nodes. So at every step, before picking up a hidden variable, you either apply a star search algorithm or breadth first search or depth first search, and then find out what is the cost. What is the cost of picking a specific hidden variable? And what is the cost? In this case, the cost might be what is the size of the joint distribution table that you're going to come up with once you pick up a hidden variable. So the larger the size, the higher the cost, right? So it actually is a search problem that you can have within Bayesian network or variable elimination algorithm. Sounds good? Okay, one more example, I promise. I know some people are quite bored right now, but one more example and we'll be done. because this is going to be extremely helpful for your homework, which is why I'm paying a lot more attention on this part. Okay, now let's just try to solve a query by having joining and variable elimination, by actually implementing variable elimination in our, once again, alarm network example. Okay, suppose that we have that query, probability of burglary given B and T, just like what we have seen before, right? Now let's just go with the like step by step and see how variable elimination actually works, right? So what we do is we look at this query and we find out all the factors that are involved. First of all the factors that are involved, right, within that probability distribution. So if you look at P of B and T, B and T, it has all these variables that are within this box, right? Do you guys understand so far? Like this one, it's actually a product of that. And then summing over E and A, right? This is what we have just seen before, a few slides before. What does the general variable elimination algorithm say? The 3 steps: pick out a hidden variable, join all the factors that has that hidden variable, and then sum out that variable. Now let's suppose that we choose A, choose alarm. Let's suppose that we choose alarm here, and then just like, do the join over all the factors, all the tables that has A. So from these, pick up the tables that has A. These 3, right? Pick up the factors that has this A. Stay awake, please. This is going to be very important to solve your homework 3 problems. So we're going to choose a hidden variable, find out all the factors or the conditional probability tables that has A, right? So we are going to pick P of A given B, P of D given A, and P of T given A, right? What does it do? What does it say? The next operation, join over all of those, right? Product. Have the product, basically A, D, and T are actually going to come up before the conditioning bar, right? And then the ones that come after the conditioning bar, we get it after the conditioning bar. So then what we do is we do the summation. Okay, except A, because you look at all the variables that are before the condition. If a variable appears at least once before the conditioning bar, just put it ahead of the conditioning bar. Just put it up. If it appears at least once before the conditioning bar, just put it ahead of the conditioning bar. If a variable never appears ahead of the conditioning bar, just put it at the back of the conditioning bar. That's how you do the join. This is a very important operation. And then after this, you just simply sum out, right? Sum out over B and E, the hidden variables, right? So we do the join P of B, P of E, and then we are actually, according to this operation, we are just going to sum out over A, right? Because we have picked A, and we get this new probability, joint probability distribution. The P of D, T, given B and E, because we have summed out A from our joint distribution. So we joined all the 3 conditional probability. Okay, I think it's way behind. We're eliminating it. We're eliminating its influence by summing out over all the rows that has that evidence hidden variable. So we are actually removing that from the equation because we're summing out. We're performing those, expansion of the equation, right? So we get with this new factor, all what we will have to do is, so you see, by joining over all these 3, we get a new factor, which is D, T, B, and E, right? I just called it F1. This is a new factor that we have received. that we have computed, right? By joining over all the entries or all the conditional probabilities that has A. All right. Next, we choose E. We look at all the entries or all the factors that has E, which is P of E, and then P of D, T, and BE. So we basically get all the variables that are behind the conditioning bar, and then we get basically all the variables that are after the conditioning bar. And we have to sum out over E in here. So after we are summing out the E with respect to E, we come up with a new factor, which is D, T, and B, F2, right? F2. And then finally, we finish with B. So we finish with B, pick out all the factors that has B, join over them, and then finally normalize. And we get our query. So all what we are doing is we find out at each step when we take a hidden variable, right? We look at the giant, the equation that is the multiplication of all the conditional probability distributions. We look at all the probability distributions or all the factors where that hidden variable exists, push that all the way to the end of the equation, push all the conditional probability distributions to the end of the equation, and then bring the summation part in there. Something like this. You see, if we look at this operation, didn't we do something like this together? So we started with that query, right? We first had to sum over. We had to sum over E and A, right? We first looked at this, basically the main equation that we had. We applied this formula, right? We found out all the factors or conditional probability distributions where A appeared, because we chose A, right, first. Where A appeared, we pushed all those factors to the end of the equation and brought the summation of A within, right, next to all those factors, because we have to sum out over R. That's not over A. So what we were doing before was we were first like joining over A, then joining over E, and then joining over A and joining over E, and then we get the probability distribution. Inference by enumeration, right? But what we're doing here is in variable elimination, the important operation is every single time you pick a variable, a hidden variable, look at all the conditional probabilities or the factors that has that variable, push all of them all the way to the end of the equation, and then bring the sum right next to it. And then simply just remove that hidden variable, do the summation. So we do this instead. So we look at all of these, right? And then push the summation. So we're actually going backwards and doing the summation first, and then doing the multiplication. Doing the elimination first, and then doing the multiplication. Like this. So you see, after the first operation, we actually found the factor 1, D, T, B, and E. Right? That's factor 1. After that, we went for the variable E, right? Like this. This is what we did. Then within this, we saw that all the factors that had E, we pushed them all the way to the end, brought the summation part, because this doesn't have E. Brought the summation part in, and then do the summation and find out another factor, which is F2. This is all what we did in the previous 2 or 3 slides. And then join, and then finally we get the P of B and F2 of D, T, and B. That is it. And this is actually what I wanted to show you guys. I'm gonna maybe have a 10 minutes so that you guys can breathe, and I can show you an example that I did in one of the previous projects that actually involved Bayesian networks. So it is one of the many tens or hundreds of different types of nanomaterials that's called quantum dot. It comes within several real life examples, actually. It is actually in some of the cosmetic applications also. It is used a lot in TV screens, cell phone screens, These are quantum dots.
Is it artificial?
It can be manufactured, it can be engineered, and they can also be natural. So by default, yeah, I think I'm just gonna show a very quick example. So what I did was we looked at basically the effects of quantum dots by having like multiple surface modifications. They can be used in many different applications, blah, 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 blah. I will also talk about one of the applications that they're used in actually cancer detection, tumor, cell destruction. They are also used in those too. So what we did was we saw the effect or the possible health impact of quantum dots. What if you inhale them or drink them in some way in the form, because they're extremely small, right? What might be their impact on the health and the environment? So we looked at all the different variables that it might have. Something like what is the surface modification that it has? What is the size of a quantum dot? What might be the core property, because you can mix some of those, engineer them, manufacture them. What might be the surface properties? Like what might be the modifications that you may have done on top of the quantum dot's surface? And then what might be the biological conditions where you may have tested that application on some sort of species, on actual organisms, on actual cells, et cetera, et cetera. And then what might be the exposure conditions? Like how long did you expose an environment or an organism or a species to that quantum dot, and at what concentration, and how toxic that quantum dot might be. So I came up with a Bayesian network structure that actually looked like this, and I saw that the diameter basically is affected by the shell. The more coatings you put on the quantum dot, its diameter is going to be affected. So I actually came up with the links of different variables within the Bayesian network. And this is the Bayesian network structure that I came up with. And then I looked at the probability distribution tables like this. IC50 is actually the concentration at which at least 50% of the population died that you saw, right? IC50 inhibitory concentration or lethal concentration. So what you see is that you can look at a combination of evidence variables. Now these are evidence variables, surface ligand, shell, asset type. You can provide some evidence and then see how toxic that evidence is, how toxic that combination is. So if you look at the first row, it says that MTT assay, zinc selenide, and amphiphilic polymer, they're actually quite toxic. The lower the IC50 value, the more toxic it is. So using some of the evidence, you can actually perform some queries and find out the answer to multiple queries that you may have. And this evidence was basically learned from the data in literature that we collected. I think I may have mentioned that it is this data basically